All right, everybody, here we go with the notes for Chapter 2, talking about sound and microphones. Let's start off with a discussion on sound. Going to get a little scientific on you here. Let's talk about what sound is in and of itself. Yeah, it's stuff that we hear, but in a scientific sort of way, the way that we describe sound is it's a vibration. It causes air molecules to be disturbed in a certain way. And you can take a look at a picture in your textbook that kind of shows how that all works. When air molecules are pushed together, which is forming high pressure, they're said to be in compression. You're compressing the air in high pressure. If you have low pressure, when molecules are being pulled apart from one another, that is called a rarefaction. So compression is when air molecules are pushed together in a high pressure environment. Rarefaction is the opposite, when the molecules are being pulled apart. And this is kind of a attempt to take a look at how that gets represented. You have that high pressure compression in this area right here. And then you have rarefactions over here where the air is pulled apart. But that is how sound is created. Those air molecules are disturbed and moved around, and the sound travels in light of those disturbances in the air. A transducer is anything that acts to convert one form of energy into another. Some examples that we could take a look at. Microphones will convert motional energy. That's the actual acoustic air particles, what we just kind of talked about. It turns that into electrical energy. From there, that energy then becomes transduced, which is changing from one form of energy to another. It could be transduced into electromechanical energy via storage in a computer file, for example. Then sent as a broadcast signal, so that's an electromagnetic transduction. It could also be transduced back into motional energy by means of a loudspeaker or by headphones. And the eardrum converts motional energy of vibration into electrical energy transmitted by neurons in the brain. So when it gets to you, it becomes electrical again. Shocking, eh? I'll see myself out. The elements of sound. A sine wave depicts sound in a graphical representation of the rarefactions and the compressions of air molecules. And again, you can take a look at this in the graphic in your textbook. Every time a wave goes through its pattern and returns to its starting point, it has completed one cycle. A cycle passes through a complete rotation every 360 degrees, and the time it takes for a wave to make a complete cycle is called an interval. So as you're taking a look at the wave in graphical form, say if you want to start at the 0 point and you watch the wave go up, and then it comes back down to 0, and then down below 0, and then back up to 0 again, that is a cycle. And the time it takes for that wave to make that cycle is what is called an interval. When you take a look at the graphs here, you can kind of see that in a graphical sort of way. That's what graphics do, right? Frequency is a measure of how often a cycle is repeated in a given period. Formerly, frequency was described by measuring those rotations in terms of cycles per second, or CPS. We still measure it that way, but we have another term that we use now. It's been replaced by hertz. So hertz basically means the same thing as cycles per second. How many instances per second that you have this measurement, this wave in the way that it's moving happening. Amplitude is the height of the sine wave. In sound, amplitude represents the greatest density of air particles, so the high point represents the compression of the air molecules. In audio, amplitude indicates the volume of the sound. The higher the amplitude, the louder the sound. So, if you have a home stereo at home, great place for a home stereo, and you increase the volume of the sound through an amplifier, well, that's what's happening here. It's making that sound louder. Amplitude, amplifier, louder volume. Let's talk a little bit more about frequency. Most sounds are really a combination of many waves of different shapes and frequencies, and they're called complex waveforms. The human ear can hear very low frequencies from around 35 hertz, like those created by the lowest notes of a pipe organ, for example, to extremely high piercing sounds up to 20,000 hertz. The low end of the scale is a deep bass rumbling, and the high end is a thin whine that's barely audible to humans. So those lower hertz tones are going to be those deeper, bassy sort of sounds, and then as you get higher and higher and higher in that hertz number, it is going to be in the upper echelons of the high notes, really, really singing soprano. Higher frequency sounds in the 1,000 to 4,000 hertz range will lend intelligibility to speech. In music, high frequencies add clarity and vibrancy. So a lot of times when you think of a sound that's coming across as bright and clear, generally that is going to be a higher frequency sound as opposed to lower notes and lower sounds that may sound a little more muddy. A decibel is a very complex measurement of relative sound levels. And the way to think of decibels is the higher the decibel rating, the louder the sound. And you see a chart on the left-hand side of your screen that shows the relative decibel level of different things that you may hear. Sustained loud sounds above 110 decibels can damage your hearing. And an increase of 6 dB SPL is what most people perceive as a doubling of the sound's volume. So it's not that it is a quantifiable in terms of like blocks, like when you double the decibels, it increases by a factor of 2. It's actually much more magnified than that. It multiplies as opposed to just adds to the volume. So that's something to keep in mind. As far as amplitude goes, broadcasters often use volume unit meters or VU meters that frequently have gradations measured in decibels. In radio, we have standardized 0 VU to equal a relative sound level that will power transmitters or provide a proper level for our recording devices. So 0 VU is the optimum volume level that we are searching for most of the time. Some other characteristics of sound. Pitch is the ear's and mind's subjective interpretation of frequency plus loudness, signifying the way we hear a frequency. Meanwhile, duration refers to the amount of time a sound exists and to the amount of time individual harmonics exist within a complex waveform. Think about if you play a stringed instrument like a guitar. When you pluck that string, you're going to get the same frequency. You're going to get the same note, if you will. But as the string stops vibrating and gets less and less in the vibration, it's going to decrease in loudness. It's going to decrease in sound level. So that's what we're talking about here. Velocity, also important. Sound travels through the air at around 1,100 feet per second or about 750 miles an hour. This is why we have issues with things like echoing and how sound dissipates the further it travels, and we'll get more into that in just a bit. As far as distance goes, in an open air environment, as the distance between you and a sound source doubles, the sound intensity will reduce by a factor of 4. You see a graph on your screen that shows kind of how that works. So the further away that you go, every time you double the distance between you and the sound source, you're going to hear that sound about 25% of the loudness that you would hear it if you were right up against it. Timbre, or sound quality, has to do with the way harmonics of a sound are combined and with the relative intensities of those harmonics. So think about how there's different nuances to the way that we hear a note being played on a piano as opposed to a trumpet, as opposed to some other type of stringed instrument, as opposed to something like a xylophone. It's the same note, it's the same pitch, but the actual quality of the sound, the way that we hear that note being manifested, becomes different. And that's what we call timbre. And this is a good point for us to take a break, and we will pick up with the microphone and talk about how it works over in part B.